So thanks for that very warm introduction, Brian. I'm going to talk to everyone today about this project, the Event Horizon Telescope project. It is this long labor of love. It's a visionary project that a number of us started a while ago. We started with about 20 people, just a few people, going to the tops of mountains to do interesting observations. Now we're 200 people. So this really is the story of a building of a team to do something that we thought was impossible. And the idea at the beginning was to make a picture of a supermassive black hole, something that had never been done before. And if we could do this, we'd be able to test Einstein's theory of gravity in the one place where it might break down the boundary of a black hole. And more than that, we'd be able to look at the physics involved at the very centers of galaxies, where we think that all of these black holes that are supermassive exist. Every galaxy has one of these at its center, and they power this luminosity at the center of these galaxies that can outshine the combined light of all the stars in the host galaxy. Now, how does this happen? And the only way to do this is to build a telescope that can peer into the center of these galaxies. So the idea was to build this Earth-sized telescope to allow us to do that. And to set the stage, I want to start off with this image, which is an optical image of the galaxy Hercules A. It's 2 billion light years away. It weighs about 1,000 times what our Milky Way galaxy does, and you're seeing the optical light. But when you look at it in the radio, you see something really interesting. Now, this should knock your socks off, providing that your socks are not on too tight. Right? These are jets of material screaming from the center of this galaxy at near light speed. They span about 1.5 million light years. To power this jet requires about 20 billion supernovae going off over the lifetime of this thing, 20 billion suns exploding. And it's not just this explosion, it's a directed explosion. And we think the only thing that can be responsible for this directed power output is a spinning black hole, accreting matter, and erupting these jets from the north and south pole along the spin axis. And the goal of the Event Horizon Telescope is to peer deeply into the center of this. But first, gravity. Okay, so in 1915, Einstein came with his theory of general relativity, and he redefined what gravity was as a geometric bending of space-time. So matter deforms space-time, and then things move in that deformed space-time. And one of the initial predictions was that during a total solar eclipse, you should be able to see the deviation of light as it just comes around the limb of the sun, and you'd see stars appear to be in different parts of the sky based on that light bending. The total extent of that light bending was about 1/2000th of a degree. And then that in 1919, Arthur Eddington, with 2 expeditions, verified, looking at this total solar eclipse, that the stars shown here in the middle of those horizontal bars had moved at exactly Einstein's predictions and not Newton's. And overnight, Einstein became a household name, redefined how we thought about gravity and the way that large-scale structure should exist in the universe. The year after 1915, in 1916, this man, Carl Schwarzschild, who has possibly the best mustache I have ever seen in my entire life, was on the front lines of World War I, calculating the trajectory of shells, going over in the military field. And he sat down and he solved Einstein's equations. I don't know how he did that. I can't even get started without a cup of coffee in the morning. He's got shells going over his head, and he solves these equations. And he shows that if you have enough matter in a small enough volume, you get to the point where you have an event horizon. And that's the point where gravity is so strong that light can't escape. This is where black holes are born. But they're really just mathematical constructs. I mean, we don't know that they exist in the universe. We don't know we can actually see one. But mathematically, they exist. And the question we have before us is, what would happen if we had infinite resolution goggles? What if we could look into the center of one of these galaxies? What would we see? Now, typically, what happens is that matter is moving around the black hole in like this circular orbit, right? So you get this pancake of material all funneling slowly into the black hole. And what Jean-Pierre Luminet found in 1979 was that you see the back part of this disk of material lensed up over the black hole. You never want to try to hide behind a black hole, okay, because people will always see you. And you wind up with this shadow feature here, whose dimensions were figured out using a solution to Einstein's equations to be the square root of 27 times that Schwarzschild radius. Let me break this down for you a little bit. If you were to see a supermassive black hole in the center of a galaxy, you'd see a shadow formed by the event horizon, and the extent of that shadow would be the square root of 27 times just a handful of fundamental constants, including the mass of the black hole. So if you want to have a real challenge and you want to see if you can calculate the square root of 27, this is what you want to do, okay? This is what Jean-Pierre Luminet drew in 1979. And I show this because this is really a convergence of art and science. He really didn't have the graphing software that we have today that can make beautiful images. This was hand-drawn with about 10,000 points on negative paper using India ink. And it came from a computer simulation, but he hand-drew this, another labor of love. And he gave us our first glimpse of what a black hole shadow might look like and what we might be able to measure to test Einstein's theories. If that was the square root of 27 across in Schwarzschild radii, Einstein would be right. Now, this is what it looks like when you really do some of the ray tracing. Now, remember I told you that the light bending on these stars was 1/2000th of a degree. Here you see full loop-de-loops around this red circle which shows the event horizon. And when you get many, many photons, a lot of light moving around the black hole, you wind up seeing this screen. And on the screen, you wind up seeing this black hole shadow. Okay? And again, the size of this is about the square root of 27 times the Schwarzschild radii. Now, why do we see so much light? That's because a lot of gas and dust is trying to get close to the black hole. But the volume is so small that you wind up, through friction, heating that gas to hundreds of billions of degrees. So in a paradox of their own gravity, black holes are some of the brightest things in the sky. And again, they can outshine the combined starlight of all the stars in that galaxy. And this is what you should wind up seeing, and this is the square root of 27 that we're after. So we're trying to build something that can see that. The problem is that these are some of the smallest objects in the universe. In order to see this, you would need to be able to build a telescope that could read the date on a quarter in Los Angeles while you're standing here in New York City. Piece of cake. Okay? Now, this is our best understanding with supercomputers of what we should be seeing. Right? Because you don't wind up seeing just the square root of 27 in a nice bright ring. There's wisps of gas coming in, there's chaotic motions of the fluid. So you wind up seeing something that's a little bit messy, but you still see very clearly that circle. And that circle is the photon orbit. Now let's go to what we actually measured. This is M87, Messier 87. It's called Messier 87 because Messier was looking for things that were not comets. He was a comet hunter. And so he started making a list of things that were uninteresting to him because they looked a little bit like comets, but they really weren't comets. So this is number 87. And this is a Hubble Space Telescope image. And if you rotate it and you carve out a little piece of it, and you see this jet that's coming out, just like the jet that I showed you before. This is in the optical. This is optical light. This is what you would see with your naked eye. And if you overlay that on the radio image, so if you had radio goggles, you also see this jet. And they overlay perfectly. But what you wind up seeing is only one side of a jet. That's because this jet is coming almost exactly towards us. And just as a train whistle gets higher in pitch when it's coming towards you and lower in pitch when it's going away from you, this is much brighter when it's coming at you. And the reason you don't see the opposite jet is because it's almost going directly into the screen. Okay, so one is coming at you, one is going away from you, one is bright and one is dim. But you do wind up seeing this ghostly shock wave here where the unseen jet is plowing into the intergalactic medium. Okay, so we're doing a little bit of scientific sleuthing here, finding out that there is actually a second jet there. When you go all the way to the center of that jet, this is the best image we have so far. So this is the best radio image we have of the center of that galaxy. And you wind up seeing this jetted structure just beginning to come out here. But in order to see the shadow, we would have to zoom in by another factor of 10 to see what's going on there. Now, it's very, very difficult to do that, okay? If you wanted to build a normal telescope, like the ones you see here, these large satellite dishes, the magnifying power is essentially equal to the wavelength of light you're observing divided by the size of the dish. So just think you want to go very small wavelengths, very big dishes to see very small things on the sky. In the parlance of radio astronomy, we call that lambda over d. That's the resolution of your telescope. And the way a normal telescope works is you've got this beautiful parabolic surface. Light waves hit that parabolic surface, and they all bounce off and combine at the same point at the same time where the focus is. And you put your camera there, and that is where you see the combined light. So in the Event Horizon Telescope, we couldn't make a telescope as big as we needed to. Because if you want to see all the way through to the center of the black hole, the center of the galaxy where the black hole is, you need to observe at wavelengths of about 1 millimeter, about that big. And if you find out, if you say to yourself, well, I want to read the date on a quarter in Los Angeles when I'm here in New York, I would need to build a telescope as large as the Earth to do that. So what we do is we effectively take these dishes, smash them with a ball-peen hammer, and take little shards of reflectivity and put them at different parts of the Earth. We use telescopes around the Earth, and we network them together to give us a telescope effectively as large as the Earth itself. This is the technique we use. It's called very long baseline interferometry. That's kind of an acronym salad. I'm going to walk you through it in just a couple of seconds. So we have these two radio telescopes on either side of the world. They're looking at the same black hole at the same time. Radio waves are coming in, and they hit one telescope first, then the other telescope a little while later. And we have these radio telescopes here that essentially work like light buckets, collecting all the photons, all the waves. And we use hydrogen maser clocks. These are atomic clocks that lose only 1 second every 10 million years to make sure that we time tag all the data perfectly. And that's because we want to bring them together later and compare them at a central facility that we call a correlator. So when you think about it, we're doing exactly the same thing as the optical dish. But instead of using the geometry of this surface to bounce things to the same place at the same time, we store them on hard disks, play them back later, align them perfectly in time, and then we combine them. And then we wind up with a telescope as big as the distance between these telescopes. It's kind of magic. I fell in love with it as a graduate student, and I never looked back. So there's really something mystical about it. I also say that the amount of data that we record is petabytes. And the only way to get all that data back to a central facility is to load it onto a 747. You can't beat the bandwidth of a 747 loaded with hard disk drives. As a matter of fact, when I take two of these modules that we use to record on and I walk across the stage, I am faster than the fastest internet in the entire world. We calculated how long it would take to get data back from, let's say, the South Pole station that I'll show you in a moment, 25 years. So it's much better to keep the disks down there while the station is closed, wait for a ski-equipped plane to go in, bring it back out. That's much faster. So there's one part that's missing, though. If you have a bunch of different telescopes around the world, you essentially just have little silver bits of this virtual dish. Thankfully, the Earth rotates for a number of different reasons. But for us, this is really a big one. And so what you're seeing on this screen over here is the effective virtual dish on the right, and it gets filled in as the Earth rotates. Right? So your telescopes in the South Pole, in Hawaii, in Spain, they all form these baselines or pairs of telescopes that sweep around as the Earth rotates and gives us a full filled dish that we can use to make an image. So this is the array that we started with. We began in the early days with just a few telescopes, the SMT in Arizona, the JCMT and SMA in Hawaii for our first measurements that showed us that there was something very, very small in the center of our own galaxy and an M87. We use now the South Pole telescope, addition ALMA and APEX in the high Atacama Desert in Chile, and our colleagues in Spain have brought in this IRAM 30-meter telescope in the southern part of Spain, and we have LMT in Mexico, and we're adding new telescopes all the time. But in April 2017, it all came together. Right? We got time on all of these telescopes, and I think this is next. And then we built these new back ends, these new bits of instrumentation to tie them all together. So the secret sauce of the Event Horizon Telescope is that we didn't use dishes that we made. We used existing dishes all over the world, and we adapted them to work together in this network of linked telescopes. So we went to the Atacama Desert where there was $1 billion telescope there, and we said, allow us to rummage around in your electronics. Give us carte blanche to do what we need to do to make this work with all the other telescopes around the globe. And amazingly, they did. Because we put together a team that was wonderful, that showed that we could do this kind of work, and they let us do these modifications. But what's interesting here is that this is Moore's law. This is the amount of data you record at each site, and this is the year. And this blue curve is Moore's law. Maybe you've heard of that. Roughly a doubling of capacity of electronics every year. It's rare in fundamental physics to be able to keep pace with Moore's law. But by hitching our wagon to 13-year-old gamers, I highly recommend doing that if you want to do some cutting-edge astronomy. we were able to increase the bandwidth of our systems in keeping with Moore's law. So this system here records 64 gigabits per second, which is about a factor of 32 beyond anything that had been conceived of before. And that gave us the sensitivity we needed to detect these black holes on these long baselines and build this Earth-sized telescope. So now I'm going to take you on a little tour of the universe. We start off at the Atacama Array, and we're going to go deep into the Virgo constellation where Messier 87 lives. And we start off going through our own galaxy, but then pretty soon we're in intergalactic space. And you see coming into focus here the beginnings of M87, like the large-scale structure around M87 where those jets are disrupting some of the activity around the galaxy. And you start seeing these jets emerge, first in the optical, and then you wind up seeing radio jets. Now we're shifting into the radio spectrum. And the center is always unresolved. You keep seeing these jets, and you don't see anything until you wind up getting to this image. This is what we found after 2 years of crunching the data. And it's fair to say that this really knocked our socks off. I mean, this was a moment that I don't think anybody in the team will ever forget, seeing this image kind of swim into view. What you're seeing here is the last orbit that light takes around a supermassive black hole. That's the ring. The center part is due to the event horizon of the black hole. That's where light rays that want to come to us first intersect the event horizon. That's the point where even light can't escape the gravitational field of the black hole. And then even more, you wind up seeing this brightening on the southern part. Now, why is that? That's because you're really seeing light speed motions of the hot gas around the black hole. And when it's coming towards you, it's brighter. And when it's going away from you on the top, it's dimmer. So not only are you seeing the paths that light takes around the black hole, you're also seeing the motions, the relativistic, the near light speed motions of gas around the black hole. This verifies Einstein's theories to the precision of our measurements to within about 10 or 20%. It also puts on very solid footing all of the simulations we've been doing over decades to see what these black holes look like. They really do look like what we think they should. And more than that, we now have a laboratory to really study black holes in a way we never had before. We've laid a ruler across space-time, and we've verified Einstein using an Earth-sized telescope. That was our reaction too. But now I want to tell you how we did it. It wasn't easy. And we really had to guard against human bias. To a child with a hammer, everything starts looking like a nail, right? So when you want to see a shadow, everything starts looking like a shadow. So to combat human preferences to see what you want to see, we split up into 4 individual teams. We had Region 1, the Americas, Region 2, more of a global team, East Asian team, and then a cross-Atlantic team, number 3 and 4 there. And each group got the data, and each group worked for about 6 or 7 weeks in complete isolation. Nobody knew what the other groups were doing. Different algorithms, different people. And the reason, as I like to say, is because it's very difficult to tell the difference between fried chicken and labradoodles. Don't laugh, this is very serious. Because when you get people in a room and they all start thinking they're looking at labradoodles, they'll all agree it's a labradoodle, but it's actually something else, right? So you really want to guard against groupthink. And if you think this is hard, then of course the Chihuahua versus blueberry muffin is absolutely just mind-bogglingly difficult. Okay, so this is why we decided that we had to split people up and send them to their different corners. Now, when we all got together after these 6 weeks, this is what we found. Now, this was a celebratory moment. I like to call this our beer moment because we didn't really know everything, but this is like we were kind of celebrating, but it wasn't champagne yet. And the reason is that these were a little bit different, but we all found this ring-like structure that came very clearly through the data. It was kind of undeniable that we had this kind of structure. And this happened at Harvard University, July 24th. This was over a year after we took the first data. Okay, so we're really doing our due diligence on this. And this was everybody at this one moment when we first got our looks at these images, a lot of smiles. And what's very important here is that there's an equal number of people on a speakerphone all around the world that are celebrating with us. This really was a wonderful group achievement, and I couldn't be prouder of the entire team that carried this out. So then we tried to make it go away. We did everything that we could to make these images disappear. Now, how did we do that? Well, on the top, you wind up seeing here different kinds of shapes that could mimic the data that we had. And I'll show you what the data looks like in a moment, and you'll understand. But we had a very characteristic shape of the data when you plot it in a certain way. And it could be mimicked by a ring, an asymmetric ring, even a filled disk, or even two sources side by side. So we took all of the algorithms that we had. We had 3 basic algorithms, and we made fake data set after fake data set after fake data set, adding all of the errors that we knew existed in our system: turbulence in the atmosphere, noisy electronics, right? Polarization filters that were not quite pure enough. We put all that into the data, and then we tested it to make sure that every time we put these fake data into our algorithms, we got exactly what we put in. When you put in a double, you get a double. When you put in this filled disk, you get a filled disk. And when we had these algorithms very finely tuned, then we made our final images, which were these. So what you're seeing here is 3 totally different methods, all giving the same answer with the same data. They're not doubles. They're not filled disks. You really are seeing a shadow beyond a shadow of a doubt. Yes, I said that. Now, so let me tell you a little bit about why in VLBI, just as with real estate, it's location, location, location. So what you're going to see here is this is what happens when you have only 2 stations. When you have Mexico and Arizona together, this is the virtual aperture, the virtual telescope I was showing you before. You wind up with 2 little points here. All you can really tell is the size of the source. You get this blob. It's when you add a 3rd station, here the Chilean station, the Atacama Desert, then since they're all kind of on a line here, all you can really tell is that it's a little bit smaller than it was before. It's when you add this outrigger in Hawaii, that's when you begin to see enough of a triangulation that this ring starts swimming into view. And after you get the European telescope, that's when you get that ring. So in the future, what we want to do is we want to add more telescopes to the array to sharpen our focus and to bring all these features more finely into detail than we had before. Now, what you're going to see here is an animation. I'm going to walk you through this a little bit. Here, you'll see the Earth rotating. And every time you see 2 telescopes active, that bar will be flashing. And you'll see, in an additive way, all of the telescopes contributing to this virtual aperture, this virtual dish. And here you'll see the actual data, and I'll show you what that means in a moment. And these are the 3 different techniques that we used. So the first thing you see is the Earth is rotating. You're collecting some of the data. And you see all the different techniques getting better and better and better in completely different ways as you add more data. Okay, and by the very end, it's still rotating here, this is the plot I was telling you about before. So what you're seeing here is you're seeing the amount of energy that is detected on 2 of these dishes, for example, the one linked here by this purple line, versus the distance between those dishes. Right? So the farther away you get, the higher resolution your telescope is. When you're over here, your telescope does not have very high resolution. Here you're looking at large-scale structure. Here you're looking at very, very finely grained structure. And to a radio astronomer like me who does Fourier transforms, does mathematics in their head when they see something like this, when I first saw this, I knew we had something. Because it's these dips. It's that dip that comes in here, the arch, and the dip down here that is a smoking gun for a ring-like structure. Right? So the data really are very clear. But we did spend a lot of time trying to make these things go away to convince ourselves that we had what we really thought we did. And then we spent some time, and actually a lot of early career researchers spent a lot of time working on methods for measuring in a very clear statistical way how big this ring was. So we had 3 different methods. I'm only showing you one here. of finding out exactly what the radius of this ring was, right? This is the radius, and this is a histogram here showing how many values you wind up getting. So we have a very clear value of the size of this ring, and these down here with the width of the ring. And this is what we were after. The shadow diameter should be equal to the square root of 27 times a handful of constants: the mass of the black hole, the distance to the black hole, the speed of light, and Newton's gravitational constant. It's so simple. It's so pure. And when we saw this swim into view, it was revelatory that you could make this prediction. It's so rare in astronomy and physics to get a prediction that's so clean that is then so purely verified. It was a pinch us moment. So where do we want to go from here? Everywhere, right? So what you're seeing here is all of the purple lines are the ones that we have currently. And all the blue lines are where we might want to go in the future. We may want to go in the future by the middle of the next decade, by 2025. And if we could do that, we'd wind up filling in this virtual mirror so well that we'd be able to make unparalleled images, not just of the black hole, but of the link to the jet that's screaming out at near light speeds. So let me show you what that looks like. On the left hand, you see a simulation done by one of the graduate students in our group, Andrew Shale. You see the black hole right here, which is in the very center, but you also see these wisps of material that link the black hole to the jet. This is how the black hole launches jets, with magnetic fields locked into the event horizon of the black hole. Imagine big strands of spaghetti whipping around at near light speed, and then charged particles are forced to move along those field lines. So like beads on a wire, they're flung out at close to the speed of light. Okay, so you wind up getting something in this direction. There's also one going behind here, but again, that's Doppler deboosted. It's moving away from us, so it's very faint. And what you wind up seeing is that with the array that I showed you before, you can reconstruct that almost perfectly. We can't do that now. So this is where we want to go in the future. And then we want to make movies. I said it. We want to make black hole movies, right? The human intellectual palate gets sophisticated pretty quickly. So it wasn't 5 minutes after we revealed this image that people were saying, what's next? So now we have to promise something else. There's going to be movies. And what you're seeing here is some visionary work done by other researchers in the team, Michael Johnson, Katie Bauman, and others. And they're working on ways to take the data we have now in the upper right. This is the array we have now. And with certain regularizers, with certain techniques that we use in the imaging process, we may be able to make images. But when we have many, many dishes, as you see down here, then we can make true movies of this spiral structure as it orbits around the black hole. And that gives us access to a completely different test of Einstein. The shadow is light moving around the black hole. These orbits are matter moving around the black hole, completely different kinds of tests. So one is the period of orbits, and the other one is the light bending around the singularity. And then sometimes you don't want to be limited by the dimensions of the Earth. If we can get a low Earth orbiting satellite, we'd wind up filling in that virtual plane here so quickly that we'd be able to make movies. So this is what we do right now. We wait for the Earth to rotate over an 8-hour period just to take one picture. If we had an orbiting satellite that moves around once every hour, we'd be able to fill that in almost perfectly. Look at that. You have almost a filled aperture. You're almost getting to the optical case. So I want to wind up here with saying that we started small. There was a time when we were working on some of this the initial experiments. We didn't know if it would work. It was a very high-risk enterprise. And some of us kind of, well, in a way, staked our reputations on being able to do this. And it did pay off because after the first experiments, we knew that we could do it. And then the joy of it has really been building a team, now 200 people strong, to make this Earth-sized telescope. And here we are in Nijmegen, Holland, at our last collaboration meeting. We represent 60 institutes, 20 countries and regions around the globe. To build a global telescope, truly, you need a global team. And what I like to say about this is that in these times of interesting divisions, this technique, this very long baseline interferometry technique that makes an Earth-sized telescope, nimbly sidesteps all of that. And it focuses only on what brings us together, true visionary science in the pursuit of something that we were told we couldn't do. So we're we have a lot of, these are the main people who are part of the stakeholder groups. I wanted to make sure that everybody knows we have a lot of people around the globe helping us. These are all the people who are supporting us. Again, we also get support from the Templeton Foundation, from the Gordon Betty Moore Foundation, and the National Science Foundation, in addition to many international funding agencies. These people have taken a leap of faith on this project. This is basic science. And if you know what is going to happen at the end of your end of your research, it's not really basic science because you know what good is going to come of it. Basic science is when you take a risk and you say, I don't know really how this is going to affect me, but I know that it is worth doing. So if you were to ask Einstein, what good is your theory of general relativity, he would not have been able to tell you. And if you had told him, look, 100 years from now, you'll be able to take your phone and using your equations, GPS will work to let you know where you are within a few feet on the ground, he would have been so excited, he would have said, what's a phone? Right? I mean, it was like so long ago, people were delivering milk with horses back then, right? So sometimes you have to wait a long time to do this, and we've had great partners that have helped us. And then I'm going to end with this. We were really surprised with what happened. We had this image, and we woke up the next day in our hotels in Washington, D.C. after the press conference. It was above the fold on all the major newspapers. Why? Why was that? We couldn't really understand it. In China, in Europe, in the United States. I think it's because, again, we tried to do something that was impossible. On the face of it, seeing a black hole is impossible, and we tried to do that. They said that there's no way it could be done. We found a way to do it with building an Earth-sized telescope. And then we built a team of people unified by a common science vision, and we gave early career researchers just the freedom to imagine what was possible, and everybody came through. And that has been really a joy. So this is a result that inspires us, and we hope it inspires you too. Thank you.